folks, welcome back to Whiteboard Science. We've got our whiteboard, we got our dry erase markers, we got our eraser, and we got a well-lighted platform here to talk about what we're going to talk about today. A subject that's somewhat centered on a topic that's near and dear to my heart, and that is flying in airplanes and aviation, etc. So, have you ever sat on an airplane, like an airliner, at a window seat, looking across the wing, and you saw all this stuff hanging down? Sometimes it's down during takeoff, landing, and it's not down at all. The wing looks normal during normal flight. Sometimes all of a sudden the airplane's vibrating. You look out the window and there's this stuff hanging up into the wind. That's what we're going to talk about today. So if you ever look at an airplane wing, it looks, if you look at a cross section, it looks something like this. Now, as I talked about in my intro video, my goal here is not to be the perfect artist. My goal is to throw some information with some visual depictions on a whiteboard as fast as possible so that you, as quickly as possible, can learn a little bit about the subject we're discussing. But yeah, these things that come down off the back are called flaps. And that's one of the things we're going to talk about today, flaps. And then also on the top of the wing, sometimes you'll see they flip up to block the wind, are spoilers. And we're going to talk about spoilers too as well. But first, let's talk about flaps. Now, real quickly, the formula that goes into how much lift that a wing produces. Here's an airplane. Again, the drawings aren't supposed to be good. I have gravity pulling down on the luggage and the people and the fuel and the airplane structure itself. I have to generate lift to counter that gravity, right? And in fact, lift has to be greater than gravity if I'm going to climb and get above, the mountains and get up into the air. And then when we want to land, then I get rid of a little bit of my lift and let gravity take over. Gravity is now bigger than lift, greater than lift, and now the aircraft descends. Well, the wing's job is to provide that lift. That is the sole purpose of the wing of an airplane, is to generate the lift to counteract the gravity. So like I had earlier, if you look at the design of a wing, it looks something like this. Now there's different wing designs out there. Some are just like your high-speed supersonic fighters, that's a terrible drawing, are just very, very thin and straight, no curvature. The Wright flyer, the Wright brothers flyer had a lot of curvature to it. It looks something like that. A lot of World War I airplanes had a design like that. A lot of it depends on what's that airplane going to be used for. What's the speed range that we think it's going to fly in. But a typical wing will look something kind of like that. In fact, that probably has a little bit too much curvature to it. And in fact, I've got another video that is called How Do Airplanes Fly, where we get into a little bit more about wing design and aircraft design. But that's a general depiction of what a wing looks like. Now, the formula for lift, which is called oftentimes the coefficient of lift, C sub L, takes into account the following. Now, I've got an equal sign here, and that doesn't mean the same as 2 equals 2 and x equals y. This just simply means, in fact, sometimes you'll see 3 lines right there, which means the coefficient of lift is dependent upon or is built around or is affected by the following. That's what that can mean right there. So one is the density, which I wrote as the Greek letter r, rho, lowercase r, but I'm just going to say density, camber angle, which is the curvature of the wing, airspeed, how fast we're flying, right? A wing that's traveling 0 is producing no lift versus a wing that's traveling 100 miles per hour. We talked about the density, the airspeed, surface area of the wing, right? A tiny little wing will produce some lift, but a bigger wing will produce even greater lift. And so those are the things that go into, and there's some other things too as well. So if I have coefficient of lift is, I'm going to use D for density. I'm going to use a plus sign. Again, that doesn't mean we're adding these things. It just means together they impact lift. We're going to say, let's just say A for, let's just use A for camber angle. And then we're going to have also speed or velocity is another term. So I'm going to use V. So we got density, camber angle, and then surface area. So let's just use S for surface area, although A would probably be a better choice. We're going to just leave it at that. Now let's talk about this. Density, flaps are used for takeoff and landing. So when I put the flaps down at some altitude and then I land at some altitude, the difference between these two is really, you know, a few thousand feet. So the density in the air between here and here really is negligible, meaning it's really not that much of a difference. So I'm actually going to take, for our discussion today, we're going to take density out of the equation, because the density of the air is, like I said, is the same from here to here. So really what we're going to be worried about is our velocity, the camber angle, and the speed, the surface area for our wing. So what do flaps do? Big picture, they do the following. They allow the wing to still generate lift to counter the gravity. And here's our wing. I'm just going to draw it real quick. But at a slower airspeed. Okay? So if I rewrite this coefficient of lift, camber angle, velocity, surface area, if my speed goes down, so I'm going to draw a little down arrow next to V, and nothing else changes, what happens to the lift? Well, we talked about that earlier. It goes down. And sometimes you want that when you want to go from high altitude to low altitude. But if I really want to get slow, then my lift is really going to go down, and I may not want to descend that fast, right? I don't want to hit the ground going fast, right? So I need to do something to bring this back up to at least not affect it. So I can increase my surface area, right? I can increase my camber angle. I can do both, or just do one of them a lot to counter the reduction in velocity. And that way there's no impact, or at least a small impact, on our lift. That's what flaps allow us to do. They allow us to still generate lift to counteract the gravity, and yet do it while we're flying slower. Why do we want to fly slower? Well, let's talk about landing. It'd be nice if I had runways out there that were 75 miles long, right? From Austin down to San Antonio. It'd be great. I could land at any speed, touch down, and just take my time coasting. Well, obviously that's not going to happen. We have runways of fixed lengths. Typically, they're 1.5 miles, sometimes 2 miles at really large airports with large airplanes. Sometimes runways are smaller. So when I land here, I want to do so as slow as possible and still be safely flying. There's a formula for what's called kinetic energy, and that's energy in motion. Oftentimes you'll hear that's 1/2 the mass of whatever it is we're talking about, a bowling ball, a golf ball, baseball, or an airplane. 1/2 its mass times its velocity squared. And that's a big deal. That means for every 10 miles per hour of speed, I have 10 squared, which is 100 extra units of energy. So if I can, let's say, if I land at 10 miles an hour, I've got 100 units of energy, plus don't forget I have to add the multiply by the mass and all, but we're just talking about velocity. But if I could land at 8 miles per hour instead, in other words, that's a 2 mile per hour difference. If I can land at 8 miles per hour instead, 8 squared is 64. Notice I've got 64 units of energy when I land that the brakes have to absorb, that the landing gear has to absorb when it hits the ground, etc. I've almost, just by reducing my speed by a mere 2 miles per hour, only 20% of my original velocity I've taken off. Guess what? I've only got 64 units, almost half now of energy that I've got to carry to the runway. So it behooves us, it's very advantageous for us to get as slow as possible. So that's what we want to do with flaps. They allow us to land at the slowest speed possible and still be safely flying the airplane. So let's take a look at our wing. There's different designs of flaps. You can look online and learn about them. Split flaps, Fowler flaps, etc. Typically, you'll have a little hinge point right here. My marker is acting up. A little hinge point here. And when the flaps come down, again, not here for the drawings, it'll look something like that. And you'll see them all the time. Like I'm talking about, if you're looking out the window on an airliner and it's close to time, close to landing time or takeoff time, you'll see this. Now, most airliners have Fowler flaps, so not only do the flaps come down, but they extend out some. So they come out like this. There's actually 2 hinge points here. So the original wing, which I'll just draw in a simple blue here, It's kind of like that. Well, what have we done? Well, we've increased the camber angle, and the camber angle is an angle drawn when you draw a line from the front end of the wing, called the leading edge, to the back end. That is your camber angle. Whereas before, the wing, if I drew the line from here to the back end of the wing without the flaps down, notice the camber angle's flat. There's really no camber angle. So one of the things I've done here on my formula, here's my camber angle, A for angle. I've increased that. So now my lift will go up. And what else have I done? Well, the wing used to be some distance from here. We'll just call it distance X to here. Well, now look where it extends. It now extends, call it Y, to here. We've added some extra distance. And of course, X times Y, that's the surface area of anything with X by Y dimensions. So what have we done? Well, we've taken a wing that at one time was this big, and we've lowered some flaps. Now, flaps don't go across the whole wing. They only go across part of it. But now I have flaps that come out like this. And of course, the body of the airplane, called the fuselage, is right here. So I've added this extra surface area to my wing. So now surface area has gone up. So if camber angle went up, surface area has gone up, then that means my lift is going to go up. But remember, we're trying to land, so what do we want to do? Because of the 1/2 mv squared, we want to get slow. So now I can slow down to a safe speed for landing. That's what those flaps do for us. They allow us to still fly the airplane safely and do so at a much slower speed than if we were just flying around from point A to B. Now that brings up a good question. If a wing with more camber angle and the flaps down generates more lift, why don't we just fly around like that all the time? Well, guess what? When those flaps are hanging down, it's like a barn door coming down into the wind, which creates a lot of drag. If you're on your bicycle or if you're in your car, you roll down your window and you hold out a poster board, you can feel that resistance. Well, the airplane feels the same thing when those flaps come down. So it's going to take a lot more engine power to compensate for that extra drag, which then turns into what? Greater fuel consumption, and now it's all about the money, right? It's all about economics. That's why airliners are in business, not to buy gasoline, but to earn a profit. So it just so happens that flaps down, increased surface area, camber angle, and all that is not the most optimum design for what we call cruise flight. When we get up to altitude, let's say 30,000 feet, we're flying from Kansas City down to Dallas, Texas, 30,000 feet, the wing with all the flaps and everything retracted, we call that a clean configuration. That's the most optimum way to cruise. But when we're going into the landing phase, a better wing design works. And in fact, this wing, when it can change its shape like that due to flaps or even spoilers like we talked about, we call that a variable geometry wing, if you will. The design we can actually change while we're in the air. Now, I'll tell you one more thing that you'll see all the time on airliners and sometimes some smaller airplanes. When the airplane's coming in to land, the wing is like this. It's got that curvature, and the flaps are down, like so. Boom. Well, the wing is actually a little bit pointed up, if you will. Kind of not up, straight up, but it's not pointed straight ahead. It's tilted up a little bit, and we call that angle of attack, AOA. And you can look that up. We're not here to talk about AOA. But what happens is the air can hit this wing, and it has to go around this curve. And for lift to be generated, the air across the top of the wing's got to flow smoothly. It can't come up here and do this and get turbulent. We call that boundary layer separation. Then we end up getting into a stall. So one of the things you'll see on a front end of a wing to help that air stay curved or follow that curve of the wing, you'll actually see the front of the wing come down like that. And those have different names. Some designs call them slats. Since this is the front end of the wing, the leading edge, sometimes you'll see leading edge slats. I've seen a term also that said LEF, leading edge flaps. I don't quite call them flaps, but that's the term I've seen before in some flight manuals. And some airplanes, these come down automatically depending upon how much you're pulling on the airplane and how slow you are and the density of the air. A computer controls that automatically. Sometimes they're manually put down. A pilot has a lever in the cockpit and he says, "Oh, it's time to land." He throws that lever and these things come down. So this increases the camber angle even more and adds even a little bit more surface area to the wing too as well. So you have your flaps, and your slats that help us for landing. But guess what? Flaps are also used for takeoff. So what I want to show you right now, note to self, is a picture of flaps in the landing configuration. Now look at these things. They are way down, big time. Now I'm going to show you a picture of flaps in the takeoff configuration. And you may have noticed this. If you're sitting prior to takeoff, flaps come down, you'll look, and you go, "Oh, they're not down very much. Is that okay?" Yeah, it is. And then when you land after the end of the flight, you go, "Whoa, they're down a lot more than they were before." And I'm going to explain to you why that is the case. Again, if I had an 80-mile-long runway, it'd be easy to just start off at the end and get to a safe flying speed at about the 3-mile point and then do my takeoff. Well, that's impractical, right? We don't have 80-mile-long runways. Very rarely do you have 3-mile runways. They're typically about 1.5 miles, if not even less. So guess what? I've got to get to a safe flying airspeed as quickly as possible as I'm rolling along the runway and reach a point on the runway that I can safely take off, or if I have an engine problem, oh no, I can bring the engines back to idle, get on the brakes, and stop before the end of the runway. And there's a lot of terms in math. We call that TOLD, takeoff and landing data, and we figure out the numbers here for this stuff. But the point is, from the time we release the brakes to the time we lift off, I don't have much time to do that, and I don't have much distance to do that. So I need to get to a safe flying velocity, speed as soon as possible. So, and that may not be as fast as I would really like to be. Maybe I want to be 50 miles per hour faster. So what can I do to my wing so that it's generating a safe amount of lift to counteract the gravity during the takeoff phase and not be really, really fast? Well, flaps, right? We already talked about that. Flaps allow you to generate a little bit more lift at a slower airspeed. Well, as it turned out, and since my airplane's going that way, I'm going to draw the wing a little bit this direction. On landing, when these flaps are down like this, remember I talked about that's a lot of drag that wind is hitting. And if the amount of lift generated, let's say if we were to generate an extra 1,000 pounds of lift, right, at full flaps, the flaps are, full. The flaps are fully down. Well, if I only put them down halfway, something like that, well, notice I don't have as much surface area out into the wind. The barn door is now a small house door, right? And suppose now even though my flaps aren't down as low as they were during landing, I still generate about 60 or more, up to 80% of the lift at half flaps or takeoff flaps, and I do it full. So I still may get 750 pounds of lift. But I have I don't have hardly the same drag that I had with full flaps. Because remember, we want to get to this point as quickly as possible. So that's why we fly with what's called takeoff flaps or half flaps sometimes. And it's different airplanes have different terms. But the point is, for takeoff, we don't put the flaps down all the way because the drag is just out of control. But we still get a good amount of lift. So it's a good trade-off between a lot of drag and a lot of lift. And so that's why we take off at half flaps. And then lastly, if you've looked out across the wing during landing, there's another thing that pops up. And again, I'm going to draw a cross section of a wing, flaps down. Why? Because we're landing. It looks something like that. And right on the top of the wing, you'll see these things flip up just like that. Now, in my other video where we talked about how does an airplane fly, we talked about lift, and we talked a little bit about it here as well. But the airflow has got to be smooth across the top of this wing. And it kind of does something like this, and we'll go into the discussion about Bernoulli's principle, Venturi effect, and how this creates a low pressure here, which means the pressure here is higher, and high always tries to get to low pressure, but guess what's in the way? The wing, right? Well, when an airplane lands and it's on the ground rolling down the runway, the wings are still generating lift, and the pilot's on the brakes. And his wheels, if I were to draw a big wheel, look something like this. They're a little flattened out, right, where the weight's on the wheel, right? Well, this surface area is all that the pilot's got to get the airplane slowed down, right? I want that thing looking like this, especially if the runway's wet, right? Or if there's snow or ice. I want as much tire in contact with the runway as possible. But if the wing is still holding the airplane up, then there's not as much weight on the tires. So as soon as I land, I don't want the wings creating lift anymore. I want all the weight on the wheels so I can get as much rubber on the ground as possible and I can get onto those brakes. And so this nice smooth airflow that I talked about that generates these differences in pressure that generate the lift for my wing, I don't want that nice smooth airflow. So I throw a big old block up here. And so when that air comes up here, it gets destroyed. We call that spoiled airflow. So instead of being nice and smooth, it comes over here and it gets real turbulent, just like if you throw a rock into a stream. And now the lift, kaput, is gone. All the weight now is on the wheels. I can get on the brakes. And because we have spoiled the lift, spoiled the airflow, those things are called spoilers. Some airplanes don't have them. Some do. Gliders that are designed to just fly forever at the slowest speed. When it's time to land a glider, that thing does not want to land at all. You'll always see spoilers on a glider. And then lastly, I'll tell you this. The max airspeed allowed by the FAA when below 10,000 feet, I'm just going to say 10,000 feet, MSL, here's the ground, is 250 knots. Call it miles per hour if you want to. 1 knot is 1.15 mile per hour. So in the world of ships and airplanes, we talk about knots and not necessarily miles per hour. But that's the max airspeed. So what if I'm up here at 15,000 feet and air traffic control says, hey, I need you down at 5, like now. Well, he dumps the nose, he dips the nose down and starts to descend. He pulls the engines back to idle. By the way, idle in the air for engines is much faster. They spin a lot faster and produce a lot more power than idle on the ground. We call it in-flight idle. So idles, those engines are still pushing that airplane a lot. Now I put the nose down, I'm in idle, but guess what? From here to here, because I'm going downhill like a bicycle, like if you're on your bicycle on the top of a hill and you decide to go down the hill, you're going to pick up speed. Well, we pick up speed, and you can't be above 250 knots below 10,000 feet. So how do I get from here to here without gaining a lot of airspeed? Well, simple. Remember, lift, gravity, they're countering each other. Well, let's just get rid of some of the lift, and we do that by putting up the spoilers. So sometimes you'll be cruising along, enjoying your apple juice or your Coke or whatever your drink of choice is that the flight attendant's giving you, and all of a sudden the airplane, it's vibrating a little bit and you can feel it. Well, they've put the spoilers up, and that turbulent, that airflow that's doing this now is actually hitting the wing. It's also going back and hitting the back horizontal stabilizer on the airplane, that turbulent air. And it can cause, well, actually it does, it causes the whole airplane to shake a little bit. So that's the end of our discussion about flaps for landing phase and takeoff phase. Yes, out of order. I did that on purpose. We take off first, then we land, right, in most cases. And then we also talked about spoilers. The purpose of flaps is they allow us to generate enough lift to safely keep flying and still do so at a slower velocity. And spoilers spoil the lift. They kill the lift so that I can either put as much weight on the wheels as possible so I can brake and get stopped within a safe distance, or they allow us to descend from a higher altitude to a lower altitude without gaining much airspeed. And that's our discussion, folks. Hope you enjoyed it. Please, if you like what you saw, subscribe, watch more of my videos. And if you have questions and or comments, leave those at the top of the threads of the thread there so I don't have to hunt and peck to try to find them. And I would be happy to entertain any questions or discussions. Thank you very much.